Hey guys, today we're going to be talking about osmosis. What is osmosis? Osmosis simply means movement of water, right? Where is the water moving? When we're talking about cells, when we're talking about containers, everything, okay? So if we look at this example right here, you have one container with just pure water and then another one with water and solute. What's important about this membrane to consider is that this membrane is only permeable to water, okay? So that solute cannot cross. So permeable only to water, okay? We defined osmosis, as we said, as movement of water, right? So we already defined that, movement of water. Now what is flux? Flux is basically the movement of the water to the solute. So you see right here this green arrow. This green arrow is representing flux. So water to the solute, right? If you want more on flux and permeability and, diffusion, we did another video on that. You can look at the video right before this. Water to solute, right? Okay. Now, thing is, water is going to be moving from high concentration to low concentration. Why is this high concentration? Because this is pure water, and this is water mixed with other stuff, right? So it's going to be going towards the solute. It's going to be drawing towards the solute, right? Because you want the same osmolarity on both sides. That's what we're aiming for, okay? However, there's an opposing force that's happening right here, okay? This represents osmotic pressure, right? So as water builds up, as water is moving from here to here, this level of water starts to increase, right? So it's getting a little higher, right? And that water on top creates a pressure that opposes flux, okay? So I'm gonna call this basically the pressure of water that opposes flux. Right? Until basically we reach equilibrium, right? So once this pressure reaches a certain point, we reach equilibrium, both the osmolarity on one side matches the osmolarity on the other side. That's it, okay? There will be no net movement of water. So yes, water will move from each side to the other side, but the amount of water on each side will not change. That is equilibrium, okay? So no net movement of water. No net movement of water. Okay, let's talk about external pressure. Let's say that we're not dealing with osmotic pressure. Let's say, in fact, what we have is these levels are the same, and then what we end up having is this container where we have this lid that basically creates this external pressure. Okay, that external pressure can oppose flux as well. It can act as though we're dealing with it can act the same way that osmotic pressure did, right? Where it's basically not allowing the movement of water because water can't come here because of this lid, right? So keep that in mind when it comes to cell membranes and when we talk about tonicity, because that cell membrane can act like a certain external pressure, okay? That's everything with that. Okay, what's the difference between osmolarity and osmolality? So first of all, what is osmolarity? Osmolarity is the total concentration of all osmotically active species, right? So it's measured by osmoles over liters of solution, right? It's basically saying how much of a certain solute is in the water, right? If you know the difference between molarity and molality, then this will make sense as well, okay? Because this really is a little bit different. It's osmoles over kilograms of solvent. So we're talking about the solvent, not just the entire solution, right? usually we end up using osmolarity. So how can you calculate osmolarity? You calculate osmolarity by knowing the concentration of the solute and then how many parts it dissociates into, right? So for example, let's say we have NaCl. If we put that in water, it's going to have Na plus and Cl negative. That's 2 parts, right? So I could then find its osmolarity by doing the concentration of NaCl times 2, right? If I'm dealing with MgCl2, that's 3 parts, right? The 2 Cl's and 1 Mg. So that's MgCl and then another Cl. So its osmolarity would be the concentration of MgCl2 times 3. That 2, it's called the Van 't Hoff factor. Okay, speaking of Van 't Hoff, let's talk about his equation, right? So the equation we're going to be looking at is pi is equal to RT times osmolarity. Okay. And really, you want to look at this equation just to understand, okay? Don't really worry about like memorizing everything. This pi is referring to the osmotic pressure that we were talking about before, right? So the thing that we talked about in the beginning of the video, osmotic pressure, okay? That's all that is. It's basically saying that this is a function of temperature and osmolarity, right? So this osmotic pressure is a function of temperature and osmolarity, right? Let's use an example to try to visualize all of this a little bit better. Let's say we have a membrane, again, only permeable to H2O, okay? There was supposed to be another parenthesis, right? Only permeable to H2O. Okay. And we got 0.3 molar of NaCl and 0.4 molar of sucrose. So if we're trying to find how many like the osmolarity of each one, okay? Remember what we talked about. We got to look at the concentration and then also the number of separate ions that are going to be produced, right? So for sucrose, there are no ions, right? So its osmolarity is simply going to be 0.4 osmos, right? On the other side, though, okay, you have a concentration of 0.3, and you have Na and Cl, so that's 2, right? It dissociates into 2. So it's got 0.6 osmos. So which one has the higher osmolarity? The one that has the higher osmolarity is this side, right? Even though this has a concentration of 0.3 and this a concentration of 0.4, this actually has the higher osmolarity. So what's going to happen is you're going to have movement of water to this way, right? You're going to have movement of water towards the NaCl because we are trying to reach an equilibrium of osmolarity, right? So does that make sense? We're trying to reach an equilibrium of osmolarity. Now, why do I have this external pressure drawn? This external pressure really, again, is trying to show me how much pressure is needed to not have a net movement of water. So let's say, for example, okay, I add a certain amount of pressure here, okay, and there's no net movement of water. How much pressure would I actually need to have this have no net movement of water, even though that there is an unequal osmolarity on each side? That would be pi, or as we said before, osmotic pressure. So if I add an external pressure equal to osmotic pressure, then I'm not going to have any net movement of water. Again, keep that in mind when it comes to seeing cells being swollen or not. Okay. When we're talking about water, specifically in biology, there are 2 ways that water moves across a membrane. Okay, number 1 is it just moves through the lipid bilayer. Why? Because it's a small polar molecule. But because it's polar, remember that polar molecules do not move effectively through a lipid bilayer. So this is going to be very little, right? But it happens. The second way that water moves through across a membrane is through water channels. What are these water channels called? Aquaporins. So aquaporins are just simply water channels. You'll see that removing a certain amount of water channels or increasing the certain amount of water channels or aquaporins is an effective way of regulating water absorption in things like the kidney. So kidney water regulation or water absorption regulation. So if you add more aquaporins or decrease the amount of aquaporins, you control how much absorption is occurring. That's why it's important. Okay, and the final part that we're going to be talking about are types of solutes, okay? What I mean by that is that there are three kinds of types of solutes that I want you to be thinking about. First one is a permeable solute. Then we go all the way to impermeable solute. Right? And then what's this middle part? This middle part is things that are kind of permeable. They're not really, they're intermediate permeability, right? So if something's permeable, it could just cross right through the membrane, right? Something that's impermeable just can't cross the membrane no matter what, okay? Another way to call this is it just reflects off the membrane, right? All right, like as if we had the membrane right here, and the solute comes, and then boom, it just bounces off, right? It reflects off of it. Okay, this one you have, and it just crosses right through. Over here, we have things that eventually cross through the membrane, right? So eventually cross, but not right away, okay? These are called ineffective osmoles. Because they don't actually contribute to something called tonicity, which we're going to talk about in a different video, but they are able to cross through the membrane. It just takes a lot of time, okay? So if we were to come up with a way to numerically discuss all of these different types of solutes, we'd use this term called sigma. So sigma is basically called the reflection coefficient. Right? Sigma is the reflection coefficient. And if you have a sigma of 0, so actually I'll move up here when I do this. If you have sigma equal to 0, okay, that means it's super permeable. If you have sigma equal to 1, that means it's not permeable. Anywhere between 0 and 1, it's intermediate permeability, okay? And these are the ineffective osmoles. When we're talking about, when we're incorporating sigma into the equation that we were talking about before, we have osmotic pressure is equal to sigma RT times osmolarity, right? So again, if you have a sigma of 0, as in it's very permeable, this is not going to create osmotic pressure. Why? Because there will be no need for a net movement of water since, the solute will move through the membrane. But if you have a sigma of 1, that means that, yes, there will be osmotic pressure that will build up, okay? In terms of these ineffective osmoles, okay, if you have something in between, it causes transient effects to water movement, but as they equilibrate their contribution to the osmotic pressure eventually approaches zero, right? Where it's almost like as if it were permeable. And that is everything for now, guys. We are going to be talking about tonicity in the next video.